2, and why not 3 and 4 qubit gates? And that's why we call it hybrid, because you wanted to use the quantum computer plus the classical computer. So this is why we need to see next slides how we can see them in a more easy way to explain to you. So as you see here, we have here on the left side and the right side. So in the left side, you see here, you wanted to find the minimum solution. You started to have superposition over all the states, but then you need to go slowly, right? You need to anneal here in order to see the tunnel effect. So you need to escape all these minimums, which are not important and they are not true that you really wanted. So you need not to jump like classical path. In fact, you need to go to the solution, which is the global and the better solution, due to the effect of the quantum tunneling. And that's why adiabatically here also it can be the same way, and you arrive to the quantum, to the adiabatic evolutions over time, and then you arrive here over the solution. So imagine you are, for example, in like an analogy here, you see you wanted to find the deepest valley, for example, in mountains landscape, right? So quantum annealing can help you to go here, because it can help you to tunnel through the mountains to reach the deeper valley here. But the classical computer, unfortunately, will let you stuck there or there or there or there. And that's why the D-Wave is the most effective, and they are really dominating this sector here. And you will see in the next slide, D-Wave company in Canada, they are helping and they are working a lot into increasing the scalability of the number of qubits to take the advantage over the quantum tunneling and to find the global solution through solving computatorial optimization problem. Now, to the right here, you see, as I said, we call them universal or gate-based quantum computers, like IBM, again, Microsoft, Google, Continuum. All those companies, they are using these methods because they are based on gates. And here you see RZ gate, Hadamard gate, and then CNOT gates, and so on, parameterized gate. So here is the way how you can describe the QAOA. As I explained, it's a hybrid approach. You see here, you have parameters, you need to optimize them, and here you have a cost function. You need to optimize, to find the minimum energy from this. So here is this circuit there, and here is implemented there. What happens here very quickly, you have the exponential over your cost Hamiltonian, and then you have mixer Hamiltonian and the cost Hamiltonian. You build your wave function there, and then you need to optimize these parameters, but you can go from depth 1 up to depth p. And that's why you need to optimize up to p parameters. You need to measure all your qubits, and then after that, you need to measure your cost Hamiltonian. So after you measure your cost Hamiltonian, you use the optimizer to update the parameters, and then back and forth, back and forth, back and forth, up to get your minimum solution. But it's not the same like here you get here, but it's in a different way using the algorithmic way, not the physical way of quantum tunneling. So here in this figure, you see that here is a kind of how we can differentiate two subsets such that the maximum connection due to the blue here, how they can be directly able to find the maximum connection of edges due to these vertices. So we will see a lot of examples in the future, in the next slides, how we can explain to you here, how to learn you, to teach you how to max cut and max click the optimization graph algorithms. That's why we call it a QUBO problem here. So as you see here is the landscape of the practical use cases in the projects. You see here we have a lot of things. We can go very quickly. Binary variables, they are the qubits, we assume them. And here on the left, we have a lot of types of what we say the gate-based, simulators, emulators, adiabatic, annealing, quantum-inspired, and hybrid solvers. So here, as you see here, there are many companies, they are working in the gate-based. So for example, IBM nowadays, they have been using around 156. This is the maximum number of qubits IBM now is tackling. But here I put 127, but this is has to be updated, of course, but this is according to my work, according to Professor Alex Khan. Also, he borrowed me this figure, so thanks to him. And then here we have a lot of emulators as well, like how to, the emulators and simulators, how to let's say the simulator, for example, how to mimic your algorithm in order to play with the algorithms, in order to find your solution, right? So you need to test it in a classical computer first, then you do it in a quantum computer. Even in a classical computer, you need to find ways in mathematics how to also deal with your number of qubits. If you enlarge 200 or 1000, then here you need a mathematical solution. That's why we call them MPS, which is a matrix product states that you are able to transform from vector space into tensor space. And that's why we call them here classical MPS simulation qubits. You go further, you have many other types of computing, like Rydberg atomic qubits, like QERA in USA. And here we have superconducting annealing qubits, D-Wave. They have been using here up to 5,000 qubit using the pure annealing. But then here you go to Dirac, and then here for the quantum inspired and hybrid solvers, that means D-Wave here are mostly using the hybrid way, how to use subsets of using pure annealer plus the other type of classical computer that help to solve some parts as well. So that's why we call it hybrid solvers. Here on this, we can find a lot of applications. They have been used, like a lot of problems they have been used using different type of computer. So I would be happy to share you in the future this PowerPoint if you are interested to look, and we can discuss more about that. So what's the state of the art of the algorithms in the optimization problems? So variational quantum algorithms, mostly of you knows that variational means you wanted to optimize your parameters in order to find your minimal solution. As you see, we have plenty of numbers of variants of the variational quantum eigensolver, which is really important algorithm to find a minimum solution for a certain physical and chemical Hamiltonian. Like chemistry and physics, you have to use VQE. Most of you, I think, have heard about it. There are many versions, but why we do have many versions? Because some of them, they don't want only ground state. Some of them, they want to reach excited states. Some of them, they want to reduce the number of qubits. Some of them use symmetry. So that's why we have different variants. The same thing for QAOA, which is a quantum approximate optimization algorithms. Here you have a lot of types as well, because you wanted to adaptively find a new version of QA that can be decreasing the number of layers, can be smoothen the optimization. That's why we have a lot of problems. Sub-problem QA, how can we have sub-layers and subsets to tackle only? We don't need all the type of nodes we are going to solve. So quantum annealing algorithm, we have a lot of things like digitized quantum counterdiabatic DCQC, for example, DQO. So this is something very important because you wanted to add mixer terms into your Hamiltonian, because you wanted to surpass your unwanted transitions, and that's why you have to use a lot of versions using the annealing problem to smoothen and to go slowly up to arriving to your global solution. There are many others here, quantum search and amplitude amplification. Many people using HUBO, which is the higher order unconstrained binary optimization problems, and a lot of global adaptive search problems here. There are many also in the red, quantum gradient based optimization. Optimization by itself, the optimizer as well. So you don't need only to find an optimized circuit, but also the optimizer by itself. It has to be clever optimizer. That's why we have different types of natural gradient and so on. And these things are important to work on. There are also quantum work-based algorithms. But mostly today, I'm going to focus on QAOA, because this is something could be simpler for the audiences to learn how we can differentiate between quantum annealer and QAOA. So you see the hardware implementations, you have to think about the number of qubits. So, okay, I showed you a lot of algorithms, but how can I see how much so far being used in the number of qubits per hardware chip? So if you see here, SSVQE is a subspace search VQE. It's important to find the excited state of a certain molecule or a certain physical problem. So far for qubit, you tell me for qubits, okay. Then, for example, if you go to adapt VQE, how to adaptively find a way to minimize your circuit. So here 25 qubits. And here you can jump into many other algorithms, many things. So I don't want to go for everything, but people have been using the real hardware here, real quantum computer, up to 127 IBM here with length P1 of your circuit. So then if you see Again, D-Wave advantage, which we call it D-Wave advantage type, they are using up to 5,000 qubits to solve only combinatorial optimization problem. But you don't need quantum, and you cannot use quantum annealing to solve excited state. That's the problem of the quantum annealing, because it only arrived to the lowest global ground state. That's why we need both. Of course, we will see in the next slide, a lot of efforts has been used in the increasing the number of qubits, but we will see the limitations and how people and researchers are putting efforts in order to overcome this challenge. So we can include a few algorithms from this table. You see, for example, here we have a lot on the left. Let's focus on many things. So you see here many types of VQE for solving chemistry problem. Then we have here a lot of QAOA and digitized counterpart diabetic quantum algorithms. And here we can go to Gover search and a lot of gradient method cluster VQE. So it's a kind of, I'm showing you here on the left side, the type of algorithm that have been so far used. But of course, there are many others, but I tried my best to see how can we study them. So here we have hardware parts. We have a lot of IBM have been using, a lot of IonQ, and a lot of IBM, D-Wave, IBM, Silicon, Continuum, IBM, D-Wave, and so on. So as you've seen, a lot of name of chips have been, a lot of versions have been updated because new qubits has been, calibrated or have been done. So that's why we see 127 up to 414, because this is the maximum qubit have been used with QA with higher order problems. So P is the number of length, just 3, 1, or 2, the length of your depth of your circuit, and the C0 depth, it means that how much I have 2 qubit entanglement gate that can make the connectivity over my circuit. So if you see the comparison over the classical computer and the quantum computer from the IBM Eagle, here it has been happening like 1,500 faster than the D-Wave spinning glass stuff. That means you have 95% of the optimal solution over all the sets you have been obtained. And that's why it's really important to see this figure. Again, I will share it for you. So you can see how many algorithms has been used and what are the platform, the maximum number of qubits, the resources, because there are a lot of limitation here, mostly because of the CNOT gates or of the TOEFL gates, because depends on the algorithms you are using, and then how we compare it with the number of qubits, with the classical computer, sorry, how much it arrived to the minimal solution. That's why we see a lot of percentage there, a lot of fastness, a lot of speed up. So I'm not gonna go through this, but this is something important for you to see. Then now we need to go to the technical part to show you how quantum annealing and gate-based are differentiated and the limitation and the challenges. So as I explained to you, the QUBO is a quadratic unconstrained binary optimization problem. So you have to minimize a quadratic function over a binary variable, 0 and 1. And then you need to use the quantum annealing QAOA, but there are a lot of application real worlds. We are going to, for example, the TSP and the VRP. Here, for example, you wanted to see many types of combinatorial optimization quadratic term you want to solve. It depends if you wanted to work in the optimization for travel, if you wanted to cross many cities at the same time, then you are going back once a time, or you wanted to work in the energy part, or you wanted to work on the healthcare part. So we are going to focus today on the financial part, how to minimize your risk and how to maximize the return back for certain banks and so on. So we are going to see that. So also the clustering and the graph problems, we are going to focus on 2 types, building up on the QUBO problem. We call them max-cut and max-click. So we are going to see in the next slide how they are going to be done. But in any case, here is the way how we are going to see in B and D, the way how we are making the graph problem into nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, the edges which are really between the variables, and how we can transform this into a combinatorial optimization problem. We call it QUBO. Then we transform it to Ising, as I explained, and then we use either the QAOA or the annealing in order to find our solution. So D-Wave, what they do exactly, they formulate the QBO and they encode the constraints as penalties. So here, we have to convert it to Ising model, as I said, and then there are different types of ships, as you see here on the right. There is Chimera and there is Pegasus, and this is what they are currently are doing. If you click on DOA, you'll see they are using these types of chain connectivity for the qubits, and that's what we call them. So what happens, in fact, they use the principle of annealing, as explained, to go slowly over the time in order to go to the ground state. The measurement happens to the qubits to many times to repeat in order to get the probabilistic sampling, and then you choose the lowest solution because it's giving you the amplitude, and then of course, as you see here, we have the seventh part, which is the hybrid workflow, because it's sometimes you have a large number of qubits, then unfortunately the D-Wave chips is not able to solve more than 5,000. We need to use the classical computer in order to help the QPU they're using, the Chimera and the Pegasus. So the state of the art of the quantum annealing, I would say, they are claiming to choose to go up to 1 million variable, which is very important to also work on 100,000 constraints. That means this is very important to add penalties, but also for the constraint models, they have been only hybrid solving up to 500,000 variable. But again, as I said, the problem is that they wanted to use hybrid. So again, they use the classical computer in order to divide the big problem into sub-problems. The only sub-problem will be solved using the QPU. Now, what's happening that once you do a lot of qubits, then you are having a problem because your number of logical qubits are going to be smaller, because you are going to reduce the connectivity over the physical qubits. So the logical qubits need to be covered among a big set of physical qubits. And if you have a large number of physical qubits, then you are not able to cover these logical qubits. And that's why the solution equality will be less. And that's why they are using the principle of the hybrid solver to partition the problem. Now, what is QAOA? As you see here on the right, we will see the problems now in QAOA. So here it's an optimization problem you wanted to solve. Let's say, for example, you have different delivery points. Okay, you are a company and you wanted to go to different delivery points at the same time, and you have two cars to go there. So to see where you have to go among these delivery points at the fastest time without having a lot of traffic jam, so you have to find a way how to use the principle of the QBO problem. And to do that, once you solve your combinatorial optimization problem, you can see which subsets which having the most traffic jam and who are not. Then you are able to control the way how you optimize the way in the faster way to arrive to your solution. This is a real life example in the routine way. So here in this A and B and C, you need to solve it as an algorithm. You map this one into a Hamiltonian problem using this. So once you map it from real X binary terms into Z Pauli's, then you are able to use the principle of quantum computer. What happens here, you need to optimize your parameters. You need to make the QAOA wave function. So you see we have subcircuit 1, subcircuit 2, subcircuit 3. That means you have a lot of layers you need to optimize. As I explained, it's a hybrid, so it will use the classical computer in order to optimize the parameters. Back and forth, up to until the results. It can give me the most optimal solution among the overall sets. And why we need that, as I said, if we have a large number of qubits, then the classical computer is not happy to able to find a lot of sets. So that's why these are very interesting. Now, in the bottom here, you see subcircuit, and why is the limitation now? The challenge is the number of CNOT gates. If I take only one subcircuit, imagine, then I map my circuit into RZ gates plus what we call it CNOT staircase. Then you have two CNOT gates here, and you need to parameterize. Imagine if you have a lot of layers, then you need to have a lot of CNOTs. But CNOTs is 2-qubit gates, they are entangled. And that's why this is the main error now in the hardware quantum computer. They need a fidelity one. Really, it's important because it's really the control of the accuracy plus the arriving of the optimal solution. That's why CNOT counts and the depth length are very important in tackling this. That's why we have a lot of efforts from big brains, from big softwares, engineers to minimize the number of CNOT gates, plus finding a smart enough optimizer to quickly find the near optimal parameters. So what happens in the max cut problem? Okay, so this is a max cut problem. Let's see on the figure here, A and B and C. So you have here 5 nodes. That means you have 5 qubits, let's say. And you have 1, 2, 3, 4, 5, 6, 7, right? You have 7 edges. Now, max cut says, I need to, like in B and C here, I need to split 2 subgroups such that the number of edges is maximized. Therefore, I need to find ways how to separate these 2 subsets. As I told you about the example of the shipping in the faster way with the traffic jam, the same thing here, it could be used for finance problem as well, to reduce the risks of the finance and to return the maximum return. So that's why we need to play with the assets in the funding way. The same thing in the healthcare. I will show you how it works. So what happens here? Look at B, for example. We have the 1 and 4 in the red. They are the 1, 1, okay? And the blue are 0, 0. We only talk now on qubits, 0 or 1, right? So once our algorithm QAOA is able to find the minimum optimal solution, as you see here on the D part, they count the number of times we have been in the green light, which is corresponding to B. That means I am in the 0, 1, 0, 0, 0, 1, 0, because the 1 is the first qubit and the 4th is the 1 qubit also, but the others are 0 qubits. That means they are the mostly optimal solution, and therefore they tell you that this is the max cut you have arrived to. So this is corresponding to B and this is corresponding to C. That means they are the most optimal solutions. But again, the main control problem here is the weight of the edges you have. So the more edges you have, the more weight on the edges you have, it controls the way how you will find the max cut problem. The same thing for the max click. The max click, you wanted to find here the largest fully connected set of vertices in a graph, okay? This is the definition. See in the graph there, you have up to 20 vertices. Okay, up to 20 qubits, let's say. Then here you have 2 dot circles, here 2, 3, and 5, and 13, and you have here 6, 7, 8, 11, 10. So here, okay, if you want to find the largest set that fully connected vertices that are fully connected, you can find this one, the largest one, 6, 7, 11, and 8, and 10, because it's the most fully connected with the others. That is very important because it helps you to potentially find the most effective one, which is the most optimal solution. Of course, you have a lot of clicks there, a lot of clicks that are composed of 3 vertices, but they are not corresponding to the optimal solution. So that's why it's very small here. But imagine if you have 5,000 variables and all of them, they are shrinked like this, they are connected, then you have a lot of problems in optimization you need to solve. And that's why we need the annealer or the quantum QAOA or the other versions in the digitalized to find our max click consists of vertices. That's it. So let's see how it works in the molecular case. Please try to focus with me on this figure. I think it will give you better shape of understanding how in the healthcare sector you can find the most interaction point between the ligands and the proteins, for example. Okay, so here I have A and B and I have protein. So in the top panel, I have the A, which are the ligands, and I have the proteins. So as most of you in the drug discovery problem, there is a process, we call it molecular docking. That means how can I bind my ligand and protein together? in order to effectively find the medicine, right? So here I have to first transform my graphical natural ligands into what we call them pharmacophore points. That means that these points, each ligand will be transformed into pharmacophore point, and that's why we call them pharmacophore. Here, the same for the protein. Once I have ligand and protein, each one is presented by pharmacophore points, I'm able to see how can I bind them also in order to have indeed here the binding interaction graph. So if you see here, there are also different types of geometry. You have to take a lot of constraints there in order to see how can you be able to representing your interaction of the ligand and the protein. Once you satisfy these conditions, between the top is the ligand and here is the protein, you are able to see how can you say, okay, I'm right, I did it. Now I can say these 2 points from here and there, for example, they can come to the point number 4, which is the hydrogen, donor and the hydrogen receptor, and many other type of ligands and proteins. That's why we say HD and HP. As you see here, my problem has been now represented by a binding interaction graph, and I have 11 qubits. I need to now see what are the most important ligand interaction protein that are good for solving, that can give me the solution, that can detect the identification of the HIV and the identifier GP in order to see the molecular interaction that can help me. Once I do have that, we go back there. We have the same problem now. We call it max click problem. You see, we go to E and we can go to QAOA or digitized counterpart QAOA in order to see how to present my problem. And then after, I need to use the quantum computer in order to solve this combinatorial optimization problem. And therefore, I would say here, look here, please, you can see that we have 12 qubits, but as we see here are the most connected qubits that are important to arrive to the optimal solution. That's what we use the max click. That's what we use the max click problem. Therefore, 1 and 11 and 0 and 6 are the most important interactions. Therefore, we compare them with the docking results in the classical. We say, okay, our results, how much they reach the optimal solution. Because, of course, you know, in the classical computer, you can know the solution, but here we are trying to validate the algorithm by itself. Let's go now to C and F. Here we already see this one. After we use the QAOA, we optimize, and then here we can see that we have a kind of figure that the graph that shows how to optimize until we arrive to the optimal solutions, and telling me this optimal solution that, okay, 1 and 11 and 0 and 6 are going to be 1, the qubit 1, it will be represented by 1, then 1, then I have 0, 0, 0, 0, 1 because of 6, then I have 0, 0, 0, 0 up to 1. That means that 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1 is the optimal solution I do have, because it has the largest probability of telling me, okay, this is finding the optimal solution. Epochs means the number of iterations in the QAOA problem. So if you compare that max cut, I ask the maximum in the MVC, are all of them, they can be used in a quantum annealing or QAOA. So both of them, they can be used in different scenarios. So now, what's the maximum number applied so far by the leading companies using variational quantum algorithms? So if we can look at IBM, as I told you, IBM, they have nowadays, let me check, 156 qubits, okay? But they have using the Heron R1 processor, and of course, they have been using this because they wanted to solve a portfolio optimization problem. That means how much we can max return and how much we can make minimum risk. So they use the SVAR. That means it's a based variational quantum algorithms, and they execute it over 4,200 qubit gates. And this is why we use to do that, because SVAR, it can help you to evaluate to see the worst cases of the value assist. Okay, so the losses of your things, and therefore this is important for the finance. And in the experiment in IBM, they have reached about 51% of success in the solution. But of course, because there are a lot of errors nowadays in the two-qubit gates, they still advancing the problem. Google, they have, as you see, that they have been using also the Willow chip and Quantinuum. Nowadays, Quantinuum, they have 56. Early version, it was, I think, 32. And they have been using it for commercial. Microsoft also, in partnership with Atomic Computing, they use 24 entangled because they use 256 physical qubits, but they have been corrected only up to 24 entangled logical qubits to use them. So the quantum advantage over a classical computer, recently QPU and QPU and IBM, they have been achieved 80 speed up over the Splex IBM, and it was 3 times over the simulated D-Wave annealing into the 156 qubit processor, as I told you in IBM, and they find a solution about 0.5 seconds versus 30 to 50 seconds. Google, as you heard very recently, 13,000 times speed up, and it's 2 hours in compared of 3.2 years that the classical computer needs. D-Wave as well have been working in the spin glass problem, and they really showed that you would need a kind of 1 million years and consuming, I think, more than global annual electricity of using classic supercomputers. So they are being using the Advantage 2 prototype in order to solve a real-world magnetic material simulation. Now we are going to finish soon, but let's go to the chemistry problems. So very quickly, quantum computing for quantum chemistry is very interesting because you have a lot of problems nowadays to find the minimum energy of a chemistry, right? For example, for benzene, for paracetamol, for many things, then for propane, many molecules, they are not yet, over the classical computing methods, they are not yet arrived to reach the energy, and that's why some of them, they suffer to find even the chemical accuracy for a certain molecule. So I tried to kind of show you here kind of molecular simulations have been used from traditional quantum algorithms, mostly from the VQE. So as you see here, we have a lot of chains of hydrogen, 10 hydrogen. Continuum, they have claimed in the Nature communication that they exactly arrive to the classical computation, which is the full configuration interaction using quanti-qubits over the chain of 2 separate hydrogen, 5 and 5, and they make it a ring, and then they are able to solve it. So let's say, for example, lithium hydride is very interesting, and many other ethylene. Here they used 28 qubits. Even here, people, they try to not arrive to the exact solution. You see here, they arrive to certain chemical accuracy, but it's achieved and it's published, but it's up to 28 until minimal basis set, because you know in chemistry we have to go to real basis set. That means real basis set like the CCP-VTZ, this is a real basis set. But for ethylene, they have been using very minimal basis set that cannot surely arrive to the real energy. So if you wish to go to VQE and to really learn from VQE, I really advise you to go to my papers. And really, it's interesting to see many other applications in drug discovery and many applications in climate change. They have been using this paper we have published. In chemistry, if some people are interested in the classical computing compared to quantum computing for quantum chemistry methods, it's really interesting to see the triple excitation. Also, the Lie algebra, I have been working in the Lie algebra to see how to also use the quantum chemistry and the quantum computing foundation, how the math can be helpful for the chemistry in order to minimize the number of qubits, how to minimize the number of using the symmetry as well to optimize very quickly. And of course, we have a lot of YouTube talks I have done. So it's very interesting really for people who are passionate like you, Quantum Africa, to really join and to really see. I am really happy to discuss with you and to talk over time together and to collaborate and to have many things together. Finally, join us. I have a small company in Paris now. It's really growing well. YWYQ, and we have OpenVQA and Open Hybrid. I'm looking for collaboration again, Quantum Africa. We have 40 contributors from different world, and we aim to science mostly. So we really like to add algorithms, and we really like to publish articles and to make collaboration. So thanks a lot for all the community of OpenVQA, all the members who are with us, and thanks everyone who are hearing us, and I'm happy for any question you want. Thanks a lot. Yes. You mean like what is the suggestion between the Cubo and the QA with not with the quantum annealing, right? Okay, so as I said, Cubo is not Hubo, so you know it's only there is a quadratic term. So the use case, as I said, is um, finance and stuff. So the suggestion is that we need to really make more benchmarks on the max cut problems to test more and more the QAA over qubits. So you have to increment the number, increase the number of qubits 2 by 2, like I did in VQE. And in this way, you can be able to test the max cut well. You have to also to work in the maximum independent set, the MIS is very important. And also there are many other types as explained, like the portfolio. So testing one by one. Also, it's very important to advise to use helpful libraries. So there are model, you have heard about model Cubo. It's a D-Wave ocean. They are having these kind of things. They compare between different type of libraries. There is also Qiskit, also OpenQA. So they have been using a lot of built on Cubo, and they have related it to QA. So they have shown a very fantastic platform. I really advise to see, but never they used them in a real life problem like here, for example, molecular docking. So that's why, as you said, I try to make the approach in the real life problem like molecular docking, but in their case, they really show how to use each optimizer by itself in a QA. And of course, it's very important again to compare D-Wave with Qiskit to see the annealer and the QA. And also, I give many tips as well on the QA to see how can you increase the length, the depth of your circuit, P, we call it, one by one, to work also in the classical optimizer by itself, because many optimizers are having different way. I would say also the warm start is very important. The initial guesses are very important. And you see here, for example, the initial guesses in your parameters are very important. If you are very smart, maybe your optimizer will arrive to the solution in 1 minute. But if the optimizer is not very smart and your start is not warm, like we call it warm, cold, then you need 2 minutes or 3 minutes to arrive to an optimal solution. Finally, I would advise also in the working for the noise handling, that means there are shorter circuit and the error mitigation method they have to be used. So this is what I see the relations between Cubo and suggestions for working between QA and Cubo. Yes. You mean the key industries like IBM and Microsoft, they are benefiting from the optimization problems? I think exploring in the field, this is very important because this mostly, I'm not talking about D-Wave now. D-Wave are really making a lot of money from that, but the others, I think they are just showing results, publications, to show that digital quantum computers are providing promising results over the classical computers, but not necessarily to show an advantage in the optimization problem yet. Some of them, they say we show they claim that they show a kind of speed up, 15,000, 5,000, but this is not really yet fixed. I mean, because there are a lot of parameters you have to compare in the comparison between classical and the quantum computers. So I would say definitely only D-Wave, I would see now they have a lot of profit from optimization problems. But the others, I'm not so sure about that. But of course, I mean, if you want to work in financial portfolio optimization problem or dynamic pricing, fraud detection, these things, some companies, they start to work on that. Yeah. How does the quantum annealing? Okay. Um, so both of them, they should arrive to the same solution, right? But the way how you are, I mean, as I said here, look at that. Not here. So this is the QAOA, okay, and this is the annealing. Both of them, they should arrive to the solution. So this is criticized by the number of qubits. So if I say the number of qubits is 50, both of them, they are going to solve the QUBO problem, which is this one, for example. So both of them, they are going to use the same method, the same cost function, but at the end, both of them, they are going to solve the problem. But then if you go for higher number of qubits, then here, even in classical computer, the QAOA may have a problem. That's why people, they go to tensor matrix product state in order to accelerate the computation. So again, annealing is faster in the number of qubits when they are very large. So this is the thing which is not only in logistics, it's only it's also in finance and so on.
Okay, thank you. So I wanted to know, is computational, is optimization about maybe finding a clever way to evade the computational equivalence law?
You mean it should be used for the law?
Is it is it just a clever way of computational equivalence law? Like if you want to run it faster, you use more CPUs or qubits.
Ah, yes. You mean like your question is in the quantum optimization, to run it faster, you need to have more, let's say we have more multi-parallel CPUs or more scalable GPUs, then it can be faster. Yes, I can tell you yes. If, for example, you use GPUs over CPUs, it will be faster, of course, because you have larger memory and then you are going to solve it. But again, I'm not talking about the limits now. It's the number of qubits who are going to be the critical points. Up to certain number of qubits, the classical computer will die. You will wait a lot of time in order to arrive to your minimal solution there. Therefore, the efforts now is to see how can these two categories, they help you. But as I said, they started to increase the number of qubits, let's say 10 by 10, up to certain limit, the classical computer fail. So this is the only thing I'm telling you, the thing how it works. I hope I answered your question about this.
Yes, I think you've answered it.
Thank you. Thank you so much. So, of course, I am going to send them for you. You don't mind send me your email, then I can share them to you. And I'm happy if you have any questions, come back to me by email or by LinkedIn. Thank you. Thank you so much. I'm really happy to talk with you again. And again, I would love to know more about Quantum Africa, and let me know how can I help if in case you need me in the optimization problems or whatever. I'm really happy to work with you. Thank you so much. Thank you so much. Have a nice weekend and have a nice happy Halloween for you. Bye.